Today what we are going to learn is the performance testing of fan. It is nothing but how do we generate a fan curve or a pump curve. The fan curve or a pump curve is nothing but the Q, the flow rate, which is either in metric cube per second or CFM. CFM is nothing but cubic feet per minute, and the head provided by the pump. It can be the static pressure head or the total pressure head. If you remember, the total pressure equal to static pressure plus the velocity pressure. The velocity pressure is rho v square by 2. If you remember from the Pitot tube. So this is the head provided by the pump to overcome the friction and any elevation requirement, any increase in velocity energy or any increase in the pressure. So this is the one in the Bernoulli's equation also we had the head of the pump or head of the fan. And typically it looks like this, the fan curve looks like this. It is monotonously decreasing. Why is it decreasing? Because the power is equal to, if you remember, the static or the total pressure times the velocity, the Q, flow rate. Okay. So in terms of the units, Newton per meter square times meter cube per second, which is Newton meter per second, which is watts. So that is the one. So the power of a pump is fixed. This might be for, let's say, a 4 horsepower pump. So if Q is higher, P has to drop. If Q is low, the P has to increase. So it monotonously decreases. Why is it not a linear line? Because the efficiency may be different at different points. That's why it's not a perfectly a linear curve. But basically you need to understand that it's a monotonously decreasing thing. You also want to remember that the system curve is monotonously increasing. The intersection of the system curve and the pump curve is the operating point. So the whole objective of this video is for us to learn how to generate a fan curve or a pump curve. Let's quickly review. There are two types, the axial fan and the centrifugal fan. The axial fan typically operate at a lower pressure and basically a higher Q. Okay. Here is the axial fan. So basically you have a shaft or a motor shaft, and here is your fan that is rotating. And the flow rate is parallel to the axis of the shaft, therefore it is an axial fan. So sometimes you put it in the van or the tube axial to increase the pressure. The centrifugal fans or the squirrel cage fan, here the flow direction is changed, it's perpendicular. And your pressures can go anywhere from 7 to 20 inches or even higher of water column. So here is the centrifugal. The air is inlet into the central area and it's sucked up and then it's blown out. So it is a perpendicular direction. So this is the point going into your screen. The air is sucked into your screen and then it pulled up by the blades and then it's pushing out. So to develop the fan curve, we basically follow the standard called Air Movement and Control Association. They developed a standard. That's what we follow. This is voluntary, but almost all fans in the market are tested and the fan curves are generated following the standard. We have the setup to do that in our lab. Maybe we can go and look it up. but we are not going to do in the lab. So basically what you do is, here is your fan. In this case, it's an axial fan. Okay. And this is the fan you want to test it. So what we have to do is we have to set up an elaborate setup. If this is the diameter, then you have a lot of relationship. So you have a little bit of narrowing down, and there is a long tube. You set up a very, very long tube, and you set up a flow straightener. These flow straighteners are nothing but, if I look at it on this way, it consists of lot of pipes. Okay. So the air is going through these smaller pipes. Basically, it makes it flow straight. That's all the purpose is. And then you are going to insert a pitot tube. If you remember the pitot tube you learned in the class, pitot tube is used to measure the static pressure and the total pressure. The difference is the velocity pressure. Using that, you can determine the velocity of the fluid. And if you multiply by the cross-sectional area, you will get a flow rate. So here are the two ends. They are connected to the two manometers, or you can connect it to the two pressure gauges. And they have given all the things about like what should be the dimension, what should be the length of the tube, all based on these diameters. And at the end, you have a throttling device to control the flow rate. So basically, you can block the whole space, or you can open up the end to allow more air to come out or less air to come out. That's how you are going to change the Q, because for doing your fan curve, what you have is Q versus the pressure. You got to change Q and get multiple points, right? So we are going to change the Q by changing the throttling valve. So if you remember the pitot tube, the total pressure is along the flow direction. Here, the air becomes stagnant. The velocity is converted to the pressure. So you measure the total pressure. So whatever you are measuring here, that is a total pressure. The one that is going on perpendicular to the flow rate, there is no velocity on that direction. So it is basically measuring the static pressure. So the difference between the two is the velocity pressure. So the total pressure is equal to static pressure plus the velocity pressure, static pressure plus rho v square by 2, okay, where things are in pascals. So I did show you this pitot tube, the real pitot tube in the lab. It's pretty small. So basically here are the gaps. So you have like a tiny holes through which the static pressure is measured. At the center is the total pressure is measured, and there are standards out there. What should be, where should be the hole be, how it should be 8 times the diameter of the inner diameter, and so on. And from here to here, it should be 16 times the diameter. Everything is standardized. You got to follow the protocol, okay? And we are going to measure the velocity, not just at one point. We are going to measure it at the multiple points along the radius inside the tube. Why? Because we know that the velocity is not uniform. So you want to estimate the average velocity pressure. So the way it is done is, so here are the dimensions given at different radius at about like a multiple directions. So if you take it as a 1, 2, 3, 4, 5, 6 directions, and you are measuring at 1, 2, 3, 4, totally you are measuring the at 24 points, the static pressure, the total pressure, the velocity pressure, and therefore the velocity at 24 points in the tube. So basically you need to drill a hole through the tube or the duct, and you are going to insert the pitot tube, locate it at the exact points. You are going to measure the tube pressure. Then you are going to move it to the next level, move it to the next level, move it to the next level, and then take it out and maybe put a duct tape to close the hole and open up the hole here, put it here, put it here, put it here, and so on. So you are going to repeat it. Okay. So we are collecting velocity, measuring velocity at multiple points. Then we need to average the velocity pressure head. Can we simply average it? Think about it. Can I really average it? Probably not. We cannot. Why? The system is designed for a laminar flow. We had a flow straightener and other stuff. So inside a duct tube under laminar flow, the velocity is like this, right? It's parabolic, right? The flow profile is parabolic for a laminar flow, right? So because it's a parabolic flow, the velocity is going to be maximum here and it's going to be pretty low on the ends, right? It's going to be different. But your velocity along the given radial direction is the same, right? So you can simply average them, right? And then you can average the next one. Maybe let's put a triangle here, right? You can average all the triangles. Maybe then you can average all the pluses. Then maybe you can average all the texts. So at the end of the step, you basically have 4 points. A cross, a triangle, and I think the next one is, I don't know what I draw, plus. Then the next one is a tech. So I basically reduce to 4 points, right? In order to average it, you cannot simply take arithmetic mean of those 4 points because the flow is a laminar flow. And the equation of the parabola is equal to y square equal to 4ax, right? That's the equation of the parabola. What that means is the velocity changes square of the radius, right? Okay. Because of that, what you need to do is, in order to, before average it, you got to linearize them. How do you linearize them? By taking a square root of the each velocity pressure and then average them. But the answer is in square root of meter per second units. So you got to square it to get the units in meter per second. So if I want to show it in the equation, if this is the velocity pressure head, let's say I am putting the H, so the units are in a units of the manometric liquid, is equal to, I first take a square root, and then I average it, and then I square the result. So when I have those 4 points, let's say the cross, triangle, plus, and the tech. So initially you are going to take a square root of each velocity. Then you are going to average them. Then you are going to square them. Okay, that's what you are going to do. So that gives you the average velocity head, and you multiply by the rho m minus rho a into g. If you think about, like, if it is a fan, if it is the density of the air, and if the manometric fluid, let's say, like, if the manometric liquid, if manometric liquid is water, then rho m is 1000 kilogram per meter cube, rho a is 1 kilogram per meter cube. Maybe you can even ignore it, right? Then PV is nothing but rho GH, right? So this is basically in pascals, right? This is in the meters, right? Right? That's what it is. PV is the velocity pressure in Pascal. PVH is the average velocity pressure head in meters. That's kind of H. And you are basically multiplying by the rho G or rho M minus rho A to be exact. Okay. Makes sense? So PV is equal to PVH into rho M minus rho F into G. In case of pumps, the manometric fluid is mercury, which is the density of the mercury is 13,600. Typically for the fluid, let's say if it is water, the density of the fluid is 1000 kilogram per meter cube. You cannot ignore it. You got to use the complete equation. Okay. So still you should use the complete equation. Okay. But it's minuscule in case of air. So in industry, the practitioners, a lot of people ignore it. So you can get the density of the air. It does change from the location to location. So typically what you do is you measure the dry bulb temperature and the wet bulb temperature. So you go back to the psychrometric chart. So you have a dry bulb temperature, you have a wet bulb temperature, you get it. And then typically you have a specific volume data, which is 1 over density. So you can determine what the density is. So typically that's how typically density is measured. Then the velocity of the air is equal to square root of 2 PV by rho air. If you remember, the PV is equal to rho V square by 2, right? So V is equal to 2 into PV divided by rho square root of, where rho is the density of fluid. In case of fan, the fluid is air, right? So we are putting square root of 2 PV by rho air. Then the volumetric flow rate Q is equal to the velocity times the cross-sectional area of the duct. So let's recall why we are doing all these steps. So if you remember the entire setup, I had a fan, am I right? I had a fan. And then I had that elaborate setup, right? And then I measured the pitot tube. And then at the end, I had a throttling valve, right? So at a given throttling valve, I measure the static pressure, the total pressure, the velocity pressure, and the velocity, and then the Q, right? And the power is equal to nothing but the pressure times the flow rate. Okay. Then we are going to repeat the step by changing the throttling valve, and we are going to repeat the steps and get basically the fan curve, which is nothing but the flow rate and the pressure head, which is the static pressure or total pressure. And it's going to look like this. Okay. So the static efficiency is nothing but the static pressure times Q. So the theoretical power equal to static pressure times Q. This is the actual power of the pump or the fan, right? So the ratio of 2 is the efficiency, and you calculate it. So if you put a total power, you get the total efficiency. Basically, total power is nothing but static pressure plus velocity pressure, right? And mostly this is what industry uses, okay? but a lot of charts do show the total efficiency too. So if they haven't differentiated it, the default should be the static efficiency. Then you are going to use the throttling valve to change the flow rate, and you are going to repeat the procedure. Basically use the pitot tube traverse across the duct and measure the velocity at the multiple points and average them after linearizing them, right, taking a square root. And then you determine the flow rate. You do have already the static pressure from the pitot tube, and you are going to plot it. And then you keep on going to do it and basically get the flow rate versus the static pressure. So that is the fan curve. That's our whole objective. So you are going to plot on the x-axis the flow rate. In one y-axis, typically you plot the static pressure and the total pressure. In the secondary y-axis, typically you plot the static efficiency, total efficiency. Okay, that basically concludes this presentation. And let's review it one more time. The whole objective is we learned how to determine a fan curve. The fan curve is nothing but the pressure head or pressure provided by the fan at different flow rate. Higher the flow rate, lower the pressure. Lower the flow rate, higher the pressure. And in order to do that, we have to have a long tube and have a flow straightener to avoid any disturbances in the flow rate so that you can measure the velocity more accurately. And in order to measure it accurately, you have to measure it at 24 points after a certain distance on the length of the tube. And then you are throttling the valve to change the flow rate. So when the flow rate is freely flowing, the static pressure is going to be low, right? If I am completely blocking the end, then the flow rate is almost zero and the static pressure on the tube is increasing dramatically, right? So that's why it looks like this, right? So that might be the static pressure. Typically the total pressure is going to be like this. And the efficiency might look like this. And the total efficiency might look like this. Okay. So basically you learned how the fan manufacturers are determining the fan curve. And that concludes this talk. Thank you.